As you know, the assessment is going to be a combination of the three units. So we've got soldering, we've got mechanics, and we've got capacitors and diodes. So it'll be an assessment of all three. So the first thing, soldering, you need to know the three ways to clean a component. So the pencil rubber, the wire brush, and the solvent, depending on how bad the oxidization is. You need to know how to protect components from things like electrostatics. So the electrostatic wristband. You need to know about eye protection, wearing the eyeglasses all the time. And obviously you need to know about things like ventilation. So safety procedures when you're soldering. So there won't be many questions on soldering because it's more a practical task, but just those basic safety and procedures. Second part is mechanics. So you need to know about levers. So the three different orders of levers. So we've got the first order, which is our basic pivot, where the fulcrum is in the middle, and then we've got a load on the end there, and then we put an effort in there. So that could be like a seesaw, could be a pair of scissors, where we've got the fulcrum in the middle. The second order is when the load is in the middle. So I always think about like a wheelbarrow. So our load is here, and our effort is here. So we lift here, this is the fulcrum. This is where it's pivoting around that point. And the third order is when the effort is in the middle. So a pair of tweezers, we put the effort in there, the load is there, thing that we're picking up or moving, and then the fulcrum is at the end there. Now you need to know which is first, second and third. Always remember the thing that's in the middle. So in the middle of first order is the fulcrum, which is F. In there it's the load. In the third it's the effort. So F-E-L, and I'll stick an X on there. So it makes flex like a flexible cord, and that will help you remember the first, second and third order. You need to know calculations involving work done. So you need to be able to calculate the work done if we lift a load. So let's say this is 100 kilograms and we're going to lift it 10 meters. Our formula is work equals force times distance. First of all, we need to find this force. If it's in kilograms, it's the mass times the acceleration due to gravity, and this is 9.81. So the force is going to be 100 kg, so 100 kilograms there, times 9.81 to give me 981 newtons. So that's the force. The distance is 10 meters. So work equals force times distance equals 981 times 10 equals 9810 joules of work done. You need to know calculations involving pulleys. So if we've got a small pulley there, big pulley there, let's turn in this. We know that this diameter, D1, we know the speed of this one, and maybe we know the diameter of this one, and we want to find the speed. Now, of all these type of calculations, if you split the diagram in two, the two that you know on this side, so D1 times N1, divided by the one you know on this side, so if we know D2, we can find N2. If we didn't know D2 and we knew N2, then that would work as well. So the two that you know divided by the one on the other side will give you the unknown. Efficiency, we need to know. So efficiency is what we get out over what we have to put in. So let's say we've got a 10 kilowatt motor and we have to supply 11 kilowatts of energy in, but we only get 10 out. It'll be 10 divided by 11 times 100%. I'll give myself a hard sum there. You can work that out with a calculator. So the percentage is always going to be less than 100 for a machine. It can't be 100% efficient. So what we get out is always going to be slightly less than what we have to put in. Moving on to capacitors, you need to know what makes up a capacitor and how the construction affects it. So you need to know that the capacitance is dependent on the area of the plates. So if we increase the area of the plates, we're going to increase the capacitance. This distance here, if we move the capacitors plates further apart, then the capacitance is going to get worse. If we move them closer together, then we'll increase the capacitance. If we change the dielectric in the middle there, we can change the capacitance. So if we go from air to say mica, then the capacitance will increase because we've increased the permittivity of that dielectric. Okay, so the dielectric is the material in the middle of the capacitor. The charge on the capacitor is Q equals CV, so you need to remember that, where this is the capacitance and this is the voltage, and the charge is measured in coulombs, and capacitance is measured in farads, generally microfarads, and we've got volts there. So if you see microfarads, remember times 10 to the minus 6. If you see milli at all, so it might have millivolts, 10 to the minus 3. It's 1,000th of a volt. So you need to be able to do those calculations using that formula, Q equals CV. You also need to be able to calculate capacitors in parallel. So they're nice and easy. If I've got 5 microfarads and 6 microfarads in parallel, then that's going to give me 11 microfarads. We just add them up. If they're in series though, if we've got 6 microfarads and 5 microfarads, the overall capacitance is going to be less than any one of them. So I know the answer is going to be less than 5. The capacitance goes down, and we need to use the formula 1 over CT, 1 over C1 plus 1 over C2, and we can use the x to the minus 1 button on the calculator. So you can put 6 x to the minus 1 plus 5 x to the minus 1 equals, and then x to the minus 1 equals. Do that on the calculator, you should get around about 3 microfarads, maybe a little bit less than 3, but around there. You need to be able to draw the charge and discharge curves for the capacitor. Now I'm not expecting works of art, but you need to get the general shape correct. Now we know it takes 5 time constants, 1, 2, 3, 4, 5, to charge. So if this is our charging voltage, there's my max there. It's my volts, and this is time. This is 1 time constant, 2 time constants, 3 time constants, 4 time constants, 5 time constants. I know that after 1 time constant, it reaches 63.2. So there's my 50. I'm going to say that's about 60 odd there. There's my curve starts there. There's my 5. There's my max. So I've got to get up to there in 5 time constants. Coming down, the current, there's my max. 1, 2, 3, 4, 5. I know it comes down 63.2%. So it'll come down 63.2% in 1 time constant. So it'll come down there, and then it'll go to 5. And all these others, this is voltage discharge and current discharge. They will both go down. Quickly down, 1 time constant, and then 5 time constants, fully discharged, no current flowing, no voltage on the capacitor. Know those charts and know which way round they go. Diodes, so you need to know what a diode looks like. You need to know that that's the anode, you need to know that's the cathode, and you need to know that the current flows this way, but it gets blocked this way. Forward bias, reverse bias. You need to know the characteristic curve. So the characteristic curve for any diode, they're all similar. So it takes about 0.7 volts to turn it on. If it's a small signal diode, it's going to be about 10 milliamps. A Zener, 10 milliamps. If it's a power diode, imagine power, it's going to be about 10 amps. It's going to be much more current. In reverse, a small signal diode might take 100 volts to destroy it. A power diode might take 1,000 volts to destroy it. A Zener, though, will be set by the manufacturer at a certain voltage to conduct in reverse. So that's a 5.6 Zener. But this will be the same, 0.7, and for a Zener, this is going to go back to our 10 milliamps. So be able to draw the shape and know what figures to put on for what diode. The last thing is the full wave bridge rectifier. So you need to be able to draw the full wave bridge. So now your 4 diodes, your AC supply here, your 12 volts, roughly 1 amp flowing, and then going to our load. So the current, when it's forward, comes through this one, down this one, and when it's reverse, this one and this one. So the idea is that the current goes through this the same way. And so we get this. And the input here is AC, but the output is DC, and it's full wave DC. We don't waste any of the waveform. Okay, so you need to be able to draw that and explain that. That's it.